that issue about the dipole moment, why did it matter? Well, this graphic down on the bottom of the slide, let's go to the top one first, because that's the electromagnetic radiation, right, coming at the molecule. That's the infrared. Well, you remember from discussions before, light has magnetic or electronic characteristics to it, and that's the arrow that's up here superimposed on the wave. When that exactly matches the vibrating dipole moment, that's when energy gets transferred. Okay? If this is minimal, in other words, a very weak dipole moment, then energy can't be transferred very efficiently. When it's a strong dipole moment down here, then the coupling transfers energy very well. So poor transfer of energy leads to a weak absorbance. Good transfer of energy leads to a strong absorbance. And also, so two things. There has to be a dipole moment, and the frequency of the bond vibration has to match the frequency of the infrared radiation. All right? Pretty simple. Kind of still talking about the basics. All right? Let's see what I got next. Oh, okay. Yeah, here's just a little bit. This is, I hope, really a review about dipole moments, because we talked a lot about that last semester. Remember what a dipole moment really is, right? It's that charge separation between two atoms. Why? Because of differences in electronegativity. So differences in electronegativity are great. You have a lot of charge separation. If the differences in electronegativity are not so great, then the charge separation is also not so great. So carbon and hydrogen, a lot closer in terms of electronegativity. So the dipole across the bond is weak. Carbon and oxygen, more different in terms of electronegativity, so the dipole is much greater. But also, remember that distance matters. It's not a static function related to electronegativity. Distance matters, and that's why the vibration of the bond matters. Because as distance increases, the charge separation increases, the dipole increases. And then when the bond compresses again, the charge separation goes down and the dipole goes down. So bond stretches, dipole increases, bond compresses, dipole decreases. And again, match of frequency is what matters. Okay? So a couple of the basics for why infrared spectroscopy is possible in the first place. Here's an example of a molecule that offers no dipole moment in one particular stretch, right? So over the arrow it says C double bond C stretch, right? So these are two carbons that for all intents and purposes are identical as far as electronegativity goes, right? You'd expect any two carbons to be very close, but in terms of their environment, both carbons are attached, of course, to each other, but they're also attached to two metals. So they're identical. That leads to no charge separation here, and so regardless of the stretching, there's no change in the dipole moment, and if there's no change in the dipole moment, there is no IR absorption. Energy can't be transferred if the dipole is not changing. Okay? All right, that's pretty much the important part of that slide. Questions or anything? I don't want to go too fast, but I also want to make sure we get to other stuff.